So we spent a couple of lectures talking about the sun and what we can learn from the star that's closest to the Earth, and now we're going to start looking further out into space and studying other stars in our galaxy and in the universe. So today's lecture is going to be all about stars. What we're hoping to learn today is how we can measure different properties of stars. So luminosity, which is how much energy they output per time, their temperatures, and how much mass, how much material those stars are made out of. So we've talked about luminosity before, and this is the total energy that is being output by the star in any given time. So luminosity is total energy output, and then brightness is the amount of that energy that you receive in some area. So if we're talking about the brightness of the sun, that would be the amount of energy coming from the sun that hits the Earth. So not all the energy that the sun outputs is directed towards the Earth, so we don't get all of its luminosity. We instead will measure a brightness, and that's going to apply for every star. So every star is going to put out its energy uniformly out into space, but only the part that's directed towards the Earth is what we will detect, and so we measure that as a brightness. So the units are a little bit different. Luminosity is energy per second, and then brightness is energy per second, and then per some area. So in this case, meters squared. And so the brightness of a star is going to depend on how far away it is and its inherent luminosity. So a very bright star might be because it's very luminous and kind of far away, or it might be not especially luminous but very close to the Earth. So just by looking at the brightness of a star, you can't say right off the bat anything about its luminosity because you have to pay attention to the distance. We've talked about luminosity, so this is the definition for luminosity: energy output per unit time. That is also called power, and it has units of watts. And for a star, we're going to use this equation to calculate the luminosity given the size of the star and its temperature. So this sigma is just a constant that you can see here. And then A is the surface area of the star. So we're going to assume stars are spheres. And so the surface area is 4 pi r squared. And then temperature will be put in Kelvin. And so just by knowing the size and temperature, you can calculate the energy output per time that the star is going to be putting out into space. And then, like we said, the brightness depends on the distance. So you basically take the total luminosity and then you divide it by 4 pi times the distance squared. So the farther away you get, your brightness will decrease, and it's not a linear decrease, it's a quadratic decrease. So brightness will decrease very quickly as you start moving farther away from the star. And the reason that it's 4 pi times the distance squared is related to this picture. So if you look at the light rays that make up the corner of this box at 1 AU, and then you keep tracing those light rays out to the 2 AU sphere, you would see that at the 1 AU mark, you would get 1 square's worth of the total sphere. But if you projected that out onto the 2AU sphere, now you have 4 squares that have the same area as the 1 square from the 1AU. Then if you go out to 3AU, you get 9 squares, and so that energy that's confined to this 1 square here gets spread out to 4 squares, and then gets spread out to 9 squares. And so that's the surface area of these spheres is the 4 pi r squared. And so that's where the 4 pi in the denominator is coming from. Is that you're looking at the surface area of these concentric spheres at increasing radius. So typically, it's easy to measure the brightness of something because that's just the amount of light that hits the Earth. So your detector can count the number of photons that hits it and use that to calculate your brightness. So then we have 2 other quantities that we can try to figure out. So we can try to figure out the luminosity, and then if we know brightness and luminosity, we can calculate the distance to that star. Or if we know the distance to that star and its brightness, then we can calculate the luminosity of the star. So you need to know 2 of those variables in the equation to figure out the third. And there's different techniques that we can use to figure out distance, and then other techniques we can use to figure out luminosity. And so just restating what the brightness is, another physics definition for brightness is called flux, and that's unit is capital F. So flux is the luminosity, the total energy output for time for the star that passes through some surface area out in space. And then when you put the surface area for a sphere in, you get the 4 pi r squared in the denominator. So an important thing to note is the luminosity of a star is not going to change based on how far away you are, but the brightness will change. So how would the apparent brightness of Alpha Centauri change if it were 3 times farther away? So let's do this one on the board. So Alpha Centauri is our closest star. And so what happens if it was 3 times farther away? So we said that brightness or flux is luminosity divided by 4 pi r squared. So we'll call R is the current distance to Alpha Centauri. And we want to see what happens if we set our, I'll call it R2 equal to 3 times the current distance to Alpha Centauri. So if you just use the current distance, we'll get this variable f. But what do we get if we instead replace the r with 3r? So the luminosity of the star isn't going to change. We just took the same star, picked it up, and moved it farther away. So the luminosity stays the same. 4 pi is just a constant. And then the only thing that's changing is we're multiplying our radius by 3. So now we get L over 4 pi 3 squared is 9, and then r squared is r squared. And so if we factor out everything that we had before, so L 4 pi r squared, now the only factor that's left is this 1 over 9. So this L over 4 pi r squared was our original flux, and so we'll call this F2. The flux after we've moved it 3 times farther away is going to be 1/9 of our original flux F. So you don't necessarily have to do all of this math, you just need to know that if whatever amount I'm increasing my distance by, I need to square it. So if I moved it twice as far away, it would be 1/4 as bright. This was 3 times farther away, so it was 1/9 as bright. And then the inverse is also true. So if I moved Alpha Centauri 2 times closer, it would now be 4 times brighter. So you just take whatever number is given and square it, and and then you have to do the conceptual part of if it's closer, it gets brighter, if it's farther away, it gets dimmer. Okay, so when we talked about luminosity, or flux, we said we could measure the luminosity or the distance. So let's focus on distance first. How do we measure the distance to these stars? One way that we can do it is by using the parallax. So we've mentioned parallax before. This was the thing that the ancient Greeks were unable to measure, and so they thought the Earth was stationary at the center of the universe. And as it turns out, stars are really far away from us, and so it is actually kind of hard to detect this parallax. So what parallax is if the Earth is moving, then at one time of the year, say July, it'll be on one side of the sun, and then in January, 6 months later, it'll be on the other side of the sun. And so if you're looking at a nearby star from different sides of the sun, it will appear as though that star has moved with respect to much further background stars. So you can see that in the pictures on the top. So the purple star is this kind of nearby star, and in January it looks like it's kind of to the left of this group of stars, and then in July it looks like it's kind of to the right of that group of stars. So because of Earth's motion around the sun, it will make nearby stars appear to move with respect to the background stars. On the sky, you can measure the angular distance that the star appears to move, and that will be your parallax angle. So parallax is an angle that you measure that tells you how much something has moved. Its apparent position on the sky has moved due to Earth's rotation around the sun, or Earth's orbit around the sun. A larger parallax angle will tell you that the star is closer to the Earth, and a smaller parallax angle would tell you a star is farther away from the Earth. And so the stars all are very far away, and so this parallax angle is quite small, and it's not really something you can see with your naked eye. So that's why the ancient astronomers were unable to detect it. You really need telescopes to be able to detect this parallax. So this is a way, certainly for nearby stars in our galaxy, that we can determine the distance to those stars. So you take a bunch of data, you look for stars that appear to move because of Earth's motion around the sun. You measure that angle in arc seconds. So remember, an arc second is 1/60th of an arc minute, which is itself 1/60th of a degree. So this is a pretty small angle. And then if you do 1 divided by that angle in arc seconds, you get a distance in parsecs. So parsec is a distance measure that we use in astronomy, and it's basically just a way to, instead of, because you don't really want to measure a distance in angles, you want to measure it in a distance. So we convert that angular measurement into a distance measurement. And just to show the relationship, so a light year is the distance that a photon will travel in 1 year, and there are 3.26 light years in 1 parsec. So a parsec is even a longer distance than a light year is. Okay, so what if we detect this parallax, we want to measure the angular distance between this point on the sky in the left picture and this point on the sky in the right picture. Earlier in the semester, we talked about how we can tell someone where something is in the sky by telling them the angle above the horizon and what direction you're facing. So I could say, look 30 degrees above the horizon if you're facing east, and you'll see some interesting object. So this is fine if you're trying to tell people who live in the same place as you where to look in the sky. But as it turns out, not everyone lives in the same place on the Earth, and so this way of measuring positions on the sky is not going to be very useful. So instead, we've come up with a way to have everyone agree on the same coordinates that something would appear in space. And so we've done that with these two new angular measurements called right ascension and declination. So you can think about this in a similar way that we have latitude and longitude lines on the Earth. So the latitude lines are equivalent to the declination angle, and the longitude lines are equivalent to the right ascension angle. So now, using these coordinates, I could tell someone what the right ascension and declination of the star is, and no matter where on the Earth they are, they can tell their telescope to point at that right ascension and declination, and we'll both be looking at the same star. So it's just an easier way to talk about something's position and not have to rely on, okay, what time of day are you looking at this thing in the east at 30 degrees above the horizon? And then let me do a bunch of complicated geometry to figure out where that point on the sky corresponds to if I'm somewhere else on the Earth. So just like the longitude and latitude lines on the Earth, these right ascension and declination coordinates have angles associated with them. So the declination maps closely to the latitude lines, so go from -90 to +90. But then the right ascension, you can measure it in degrees, you can also measure it in hours. So this is a consequence of the Earth rotating 24 hours in a day. So we map the different angles along the celestial equator to different hours in the day. And so this map of the sky is basically a projection of this is the celestial sphere. So this is the 0 declination line is the celestial equator. The 90-degree positive and negative are the celestial poles. And so you can tell someone where in space to look using these coordinates. And it also makes, when you measure parallax, it makes that a lot easier. So you can, if you're looking at the same star that looks like it moves in the sky, you can just measure its Aryan-Dec in January and then its Aryan-Dec in July, compare those two positions and calculate the angular distance between them. Okay, so that's how we'll measure distance for nearby stars. Later in the semester, we'll talk about distance to farther away objects. But now let's move on to how we might measure the luminosity of a star. So the most luminous stars, and everything is going to be measured relative to the sun now. So 10 to the 6, so 1,000,000 times the luminosity of the sun will be the most luminous stars. Then we have stars that are 1/10,000th as luminous as the sun on the lower end. So there's a very large range for the amount of energy output per unit time that a star can generate. Okay, so this will bring us to a way that we measure the brightness of stars. So instead of so we can use luminosity, but when we're measuring things, especially with your naked eye or with a chip on a detector, it can be more convenient to measure things in magnitudes rather than in normal, like, standard units of measurement. So the lowercase m is the apparent magnitude of a star, or similar to its brightness, and then capital M is its absolute magnitude. So the absolute magnitude would map to the luminosity, and the apparent magnitude would map to the brightness. And they are just different by one being lowercase and one being capital. So this magnitude scale is very convenient when you're comparing two stars to each other. And so if I know the magnitude of one star and the magnitude of another star, then they have to satisfy this relationship. And the way that this system was first developed was we picked a star as our reference star and compared all the other stars to that star. So we picked a very bright star, Vega, and we set Vega's magnitude equal to 0, and then you scaled every other star off of the brightness of this one star. Then if you know the distance to those stars, you can convert this lowercase m to a capital M. So you can convert the apparent magnitude to the absolute magnitude. So these equations at the bottom let you convert the apparent magnitude to fluxes, and then you can convert your absolute magnitudes to luminosities. And so this magnitude system is always a comparison between different stars. So I can tell you the magnitude of a star, let's say 20, and that's just a relative measurement but it will let you compare the brightness to other stars nearby. And so this factor of 2.5 is important, and then this logarithmic scale is important. So the way the logarithm works is if I put and this should be log base 10, if I put let's say I put 100 inside of this logarithm, then the logarithm of 100 is equal to 2. And so then I'm taking 2.5 times 2, and I would get the difference between my two magnitudes to be equal to 5. So what that's telling me is that a difference in magnitude between two stars of 5 will correspond to a flux ratio of 100. This magnitude scale is a way to compress a very large range of fluxes and luminosities. Like we saw, luminosity went from 10 to the 6 all the way down to 10 to the minus 4. So that's a very large range of values, and this logarithm allows you to compress that into a much more manageable range of, let's say, so this was 10 to the 6, 10 to the minus 4, so that would be 10 to the 10, so log 10, so that would be a magnitude difference of just 25. So it's much more manageable to do mental math when your magnitude range is just 25 rather than try to do 10 to the minus 6 compared to 10 to the minus 4. So that's the motivation for using this magnitude scale. Knowing these magnitudes, we can talk about what we can see with our eye and compare that to different types of telescopes. So with our naked eye, we can see visible wavelength sources down to maybe magnitude 6 or magnitude 7. So that'll let you see planets, some bright stars, but not a ton else. Then we can, with telescopes on the ground, you can have long exposure times and you can have really big collecting areas for your telescope, so you can get to about magnitude 27 and really the best top of the line scientific observatories in the world. I think at our observatory we can get to probably magnitude 20. And then for space-based, you can get even better because the atmosphere is not blocking any of the light and there's no turbulence in the atmosphere to worry about, so you can get down to probably magnitude 32 with your space-based telescope. So that's luminosities, but we can correlate those luminosities to a temperature on the surface of a star. So we collect spectra of different stars. So remember, spectra, we take all the light coming from a star and we measure how bright each wavelength of light is for that star. And it turns out that different absorption lines, so different black lines in our spectrum, will correspond to different elements in the atmosphere of that star. So by looking at the spectrum of the star and finding these absorption features, we can determine what kind of chemical elements have to be in that star's atmosphere. Different chemical elements will have different properties depending on their temperature. So the biggest thing is your ionization level will change depending on temperature. So for something like hydrogen, it only has one electron, and so it's easy to get that electron out of your atom, and now you have an ionized hydrogen atom. And ionized hydrogen will have a different spectrum compared to not ionized hydrogen. But there's lots of different elements in the periodic table, and they will all have a similar behavior, where if they're ionized, they have a different spectrum than if they're not ionized. And in the lab on Earth, we can figure out what temperature we need to put those different chemicals at in order to ionize them. So if we detect any of these ionized elements, so for example, ionized calcium, if we detect that in a star, then we know that its temperature is somewhere between 7,500 and 6,000 Kelvin. So by studying the spectrum, we can figure out what temperature the surface of that star has to be. So we talked about this a couple of times. As you increase the temperature of something, it will emit different kinds of photons of light. And if you take that over a large range of wavelengths that you would have for a black body, like different temperatures of stars, you'll get what's called a black body curve. So for the 3,000 Kelvin star, you get this red curve. For the sun, you get the orange curve. And then for a very high temperature star, you get this blue curve. And where the peak of this emission occurs will be at different wavelengths depending on the temperature of the star. So this is another way that we can figure out what the temperature of the star is, by looking for the peak of its energy output. And then using Wien's law, we can calculate exactly what that temperature is. So if you see the temperature of a star peaking in the visible wavelength light range, then it's going to have a temperature that's similar to the sun. And so in this equation, we would just rearrange it. We are measuring a max wavelength, so put that in the denominator, and then you can calculate the temperature of that star. So you can measure temperature by making this black body curve and finding where the peak output is, or you can look for those different ionized chemical signatures in the star's spectrum. And so when we do these different measurement techniques, we find that the hottest stars are about 50,000 Kelvin, and the coolest stars are about 3,000 Kelvin. And the sun's surface temperature is about 5,800 Kelvin. So for all of these measurements, the sun is pretty low on the low end of things. It's not the coolest, it's not the least luminous, but it's nowhere near the hottest or the most luminous stars. So the level of ionization of these different elements will tell you the temperature of the surface of your star. So obviously the lowest temperature you have solids, liquids, and gases. And then as you keep increasing the temperature, you can ionize gases, which is what a plasma is, and you'll get different types of chemicals that will become ionized. And so, for example, this is what the sun's spectrum looks like, and all of these black lines are different absorption features. So you can go through all of these black lines, figure out what chemical is responsible for that, and some of them will be ionized gases, and on the lab on Earth, figuring out what temperature you need to get those ionized gases, you can figure out what temperature you need in the sun's atmosphere to have those kinds of gases be ionized. So people have done all this work, and we'll talk about them in a second, and they came up with this spectral classification for different stars. So O-type stars are the hottest, so they have above a 30,000 Kelvin temperature. Then B, A, F, G, K, and M. So G is what the sun is, so not all the way at the bottom, but certainly not at the top of the classification range. So which of these types of star is going to be the hottest? So I'll show you the mnemonic device that people typically use to memorize this. So it's O, B, A, fine, girl or guy, kiss me. I think that's probably a bit of a dated mnemonic device. So if you can think of a better one, you can let me know. So this is the order of the spectral types of stars, starting from the hottest on the left, and then the coolest on the right. And so for this problem, the B is the hottest spectral type in this list. And so I mentioned there were people that did all of these calculations for all of these stars and doing the spectral classification, and these were the so-called calculators. So before electronic calculators were invented, you had to have people doing this. And so Annie Jump Cannon and the rest of these women were the calculators of that time. And so it's good to highlight people other than old white men who made important contributions to astronomy and science in general. Okay. The next thing that we can measure, so we've talked about, you can kind of get the luminosity if you know the temperature of the star, and you can measure brightness just with your eye or with the detector on your telescope. And now we're going to talk about how you might measure the mass of a star. So we can measure the mass of the sun by seeing how the planets orbit the sun, but it can be very hard to detect planets orbiting other suns. But there are stars that exist in binary systems. So these star systems formed and they had enough mass and gas that two stars formed instead of just one. And so these two stars are orbiting each other. And when the two stars are kind of next to each other, viewed from the Earth, we're getting the light output from both stars. And so that's the most light you're going to get. If one star passes in front of the other star, now we're getting all of the light from star B, but we're not getting all the light from star A because it's getting blocked by star B. So the light output's going to dip a little bit, then we go back to max brightness, and then when star B is behind star A, now we're only seeing star A and not star B, so we get another dip. So you can look for the brightness of a star system, and if you see these kinds of dips, then you can infer that it must be a binary system, and then timing when these dips occur, you can figure out the period of the orbit of the system, and then using Kepler's laws, once you know the period, you can try to calculate the masses of the stars in the system. So there's 3 different ways that we can detect binary star systems, and about half of all stars that we detect are in binary systems. So we could have evolved on a planet that instead of orbiting one star, we were orbiting 2 stars, and you could imagine the different sunsets and sunrises you might get in that kind of system. So if half of all stars are in binary systems, which type of system is the most common in, say, most common in our galaxy? So is it a binary star system, a single star system, or do they occur at about the same rate? Okay. So let's do an example. Let's say that there are a total of 8 stars in our sample. Okay, so there's 8 stars. Half of them are in binary systems. So there's 4 that are in binary, and then there are 4 that are in not binary systems. Let's say single star systems. the binary system, in order for it to be a binary, there has to be two stars in one system. So this would be system 1 and system 2. But then for the single star system, you just have one star in each system, so there's a total of 4 systems. So this is kind of a math logic trick. So even though half of all the stars are in binary systems, the most common type of system is still a single star system. So it's not surprising that Earth is in a single star system. So the different types of binary systems, we can detect visual binaries where you can just see both stars and they are moving with respect to each other, and so they're not just two stars that happen to be close to each other in space, they're actually orbiting each other. This just has some interesting GIFs of what different orbiting binary systems might look like. So if they have similar masses, then they'll just orbit the common center of mass of the system. If one is a lot bigger than the other, it will be closer to the center of mass, but they're still both orbiting the center of mass. As you get a bigger mass discrepancy, the larger mass will orbit less, and the smaller mass will orbit farther away from the center. But then you can get really crazy systems too. So these are both orbiting the center of mass of the system, but now they have elliptical orbits instead of circular orbits. And so there's some variety in how your binary systems might behave. And then there's the eclipsing binaries, and just like with the exoplanet transits, the same kind of logic will apply to the eclipsing binaries. So if you have a star pass in front of another star in its orbit around that star, then you get these dips, and you can detect that using your detectors. And you can also do spectroscopic binaries. So if the Earth is to the right of this image, then as star B is orbiting star A, sometimes it's going to be moving towards the Earth, and sometimes it's going to be moving away from the Earth. And due to the Doppler effect, the absorption or emission lines will get shifted bluewards if it's moving towards the Earth, or redwards if it's moving away from the Earth. So we have several different techniques that we can use to try to find these binary star systems. And then once we have detected these systems, we can study them to figure out their periods, and then using Kepler's law as modified by Newton, we can try to figure out the total mass of the system, and if we know the spectral types of one or both of the stars, then we can try to figure out the individual masses. And so you really need 2 of these 3 variables in order to get the complete picture. So you can get the orbital period from the, for example, an eclipsing binary. You can get the orbital velocity from a spectroscopic binary, and then you can use that to calculate the orbital separation. Or if you know the distance to that star system, you can use geometry to calculate this separation distance, and then you only need orbital period or orbital velocity to calculate the remaining variable. And then this is again assuming circular orbits, because the math is easy to do for those. So when we look for these binary systems and we use those the orbital properties to calculate the masses, this is what we end up with. The most massive stars are 100 solar masses, and there are a few that are above 100 solar masses. And then at the small end of the scale, there are ones that are 0.08 times the mass of the sun. And so this, the upper limit is kind of nebulous. It's not a very exact number, but this low end of the mass scale is a very precise number. And so next time when we talk about star formation, we'll talk about why this is such a precise number. And again, the sun is somewhere in the middle of these extremes. It's not all the way on the small end, but it's nowhere near one of the more massive stars that we see. So for luminosity, if we know the brightness and the distance, we can calculate the luminosity, and we can use parallax to figure out the distance to nearby stars. If you can get a good enough spectrum of your star, then you can try to figure out its temperature and spectral type by figuring out what chemicals are ionized in the sun's atmosphere and at the surface. And then if you can find binary star systems, you can use Kepler's third law as modified by Newton to calculate the masses of the stars in that binary system.